All right. So we are going to continue our discussion on finite state machines today. Date is Tuesday, November 24th, and this is your last class before the Thanksgiving break that starts tomorrow. There's not going to be a studio session tomorrow because of the break. So the next session will be the Wednesday after you come back. So that's going to be December 2nd. That's when your Studio 7 will be due. Your homework 10 is due on Gradescope tonight. Homework 11 will be posted later today, and it will be due after you come back, not immediately, but the Friday of that week. Like I said, Studio 7 is due the Wednesday after you come back. Studio 8, which is your last studio, is available on Piazza. It's a LogicWorks studio that's due the last Wednesday of the semester, which is December 9th. Quiz 22, your daily quiz, is available on Gradescope for you to answer. So please do that. Take a minute or so to answer those questions. All right, so just a quick recap about what we are doing here. We were talking about two types of finite state machines, Moore and Mealy. The Moore finite state machine is a synchronous finite state machine because the outputs of that finite state machine can only change soon after the active edge of the clock, because it only depends on the state of the sequential elements. In this case, we are using flip-flops as our sequential elements, so it depends on the outputs of the flip-flop. However, a Mealy machine is a little bit more useful in a general case because it's asynchronous in that the outputs can change based on two things. One is the input changes. So input changes and then the output of the finite state machine would change immediately. There's a direct relationship there. And the other way the outputs can change here is based on the state of the flip-flops, very similar to a Moore machine. So a Mealy machine is a little bit more useful, and actually we'll see more benefits of a Mealy machine, and we'll see how it can be simplified more than the Moore machine, which means that it's going to be a little bit efficient in terms of implementation. We were talking about this particular example here in which we were designing a vending machine. That was our finite state machine we were designing. The vending machine takes in two types of inputs, nickels and dimes, and vends an item for 15 cents. And one of the assumptions that we made was that the machine keeps the change. So if you were to give it 2 dimes, say 20 cents, then it would keep the 5 cents change, but it would still vend you the item. We were ignoring the clock for this example, and we were transitioning between the states when a user inserts a coin. Can be two types of coins here. And another assumption that we made was, if you want to start all over again, if you want to start the machine again from wherever you are, from whichever state you are, if you want to restart the vending process, then you would need to hit the reset button. So those are the assumptions that we made, and then we drew up this particular state diagram. And in this, we had 4 states, and we called them S0, S1, S2, and S3. Those 4 states were used to indicate how much money is currently put into the vending machine. So we use 0, 5 cents, 10 cents, and then 15 cents. And the output, which is to vend an item or not vend an item, was dependent on the state your finite state machine was in. So right away, when you see an output that is attached to the state, you know that it is going to be a Moore machine. And as you get the inputs of, say, nickel or dime, you would be transitioning from one state to the other. So for example, if you are in state 0, where you have no money into the vending machine, and if the user enters a nickel, a coin, that will help it transition from 0 to 5 cents. In both those states, you're not vending an item, so output is still 0. And then we considered all the different types of inputs. What if you get a nickel? What if you get a dime? What if you do not get anything? No nickel, no dime. Or a reset. You do a self loop to state 0. And then we went through all the cases. In state 3, that's when your output or vending mechanism should be activated so that the user gets the item. There's a question online, when we went, wouldn't we go back to the zero state since the user needs to pay again? No. So that's the absolutely the same reason we had that assumption, right? So we wrote that assumption just so that we have a very simple case to deal with. However, if you have those kind of realistic situations come into your finite state machine design, then your design kind of gets a little bit more complicated, but that's what happens in real vending machines. This is just an example in which we are dealing with limited number of states, only 4 states here. So a user would have to literally press the reset button to come back over here to state 0. All right, let's move on and look at, well, this was the same state diagram, but presented on a slide in which we are highlighting the current state of the finite state machine, the output, vend or don't vend, that is linked to the state your vending machine is in, the finite state machine is in, and then we also indicate the state transitions. Those are inputs that cause a transition from one state to the other, indicated by the arrows or the arcs. N or D, that simply means either nickel or dime would result in a transition from 10 cents to 15 cents. And complement and decomplement, that is both are N complement and D. So you're not giving a nickel and you're not giving a dime. All right. Now let's talk about state encoding. And the basic idea is, because we have states S0, S1, S2, S3, we could encode them in various ways. The simplest way would be S1 and S0, right? Those suppose we have 4 states, and we call them S0, S1, S2, S3. Now, instead of having 4 states called S0, S1, S2, S3, what we can do is we can encode them into just 2 bits, S0 and S1. And we can say they could be 0, 0, 0, 1, 1, 0, and 1, 1. This is one way you could do the state encoding. So essentially that is sort of the 0 cents state, that is 5 cents, this would be 10 cents, and this would be 15 cents. And this is, one way of doing it. Doesn't have to be this exact same encoding. However, if we were not paying very close attention to low number of states, what could happen is somebody would come in and say, I don't have 4 states, I in fact have 15 states, or actually 16 states, right? Those could be 0 cents, 1 cent, 2 cent, all the way up to 15 cent. Now, obviously, this is one possible state assignment. However, it's not very useful in our case because we are not even dealing with 1 cents. We are just dealing with nickels and dimes. But as far as the design process of this vending machine is concerned, one designer could choose this. And if they do choose such a state assignment, they would not only have a complex and more costly design, they would also need to deal with many unused states, right? So clearly in this, we are only using 4 states. Rest of the 12 states are not being used. So could do it, but it results in a lot more states and a complex design. So you should pay some attention to how do I minimize the number of states that I need to deal with. Often in design problems, you will face this situation of state assignment. So you would have to think a little bit about what are you going to assign as your states. Let me give you an example here. And this is not related to Studio 8. This is not related to that. I'm just talking about a general example in which such a situation could occur. Suppose you're designing an elevator controller, right? And if you're trying to design an elevator controller, which is again a finite state machine design problem, one designer could come in and say, I will have 8 states. Each of those 8 states represent which floor the elevator is at currently, right? So 0 and then 1 would be first floor, the second state would be third floor, and so on, right? So state representing each floor. That's one way of doing it. And another user comes in and says, you know what, let's be a little bit more conservative in terms of number of states. So let us just have 3 states: elevator moving up, elevator moving down, elevator not moving, right? So they could design a very efficient finite state machine which works exactly the same way. However, they would have done it in a very cost-effective manner, right? So you would have to think a little bit about what you are going to use as the states. So I hope that is helpful discussion. Let us take a few questions here. The arcs are the inputs. Well, the arcs are essentially indicating state transition, right? So you go from, let me show you this. You go from state 1 to state 3 when a user enters a dime. So dime in this case is a user input that is causing the transition from state 1 to state 3, right? So the input is causing the transition, but the output only changes after it reaches state 3. So that's after the user enters D. All right, let's see. So that's why vending machines usually accept limited currencies. Yes, so that you have a limited number of combinations to deal with. Could you have 2 states, success and failure, for the vending machine? You could, as long as you, so success and failure is more towards the output, right? That's indicative of the output. Wend or not wend, we do have that, right? But that's our output. So you would have to think about what kind of states you would want to deal with, because you have to stay in that not wend state for a long time, right? So you would have to deal with how you're going to design the machine to do that. But yeah, but that's possible. You can go lower in terms of number of states. I'm not sure if it is valid, if you can do that for this particular finite state machine, but for other finite state machines, you can certainly spend some time thinking about how do you reduce or minimize the number of states, because that is directly linked to the number of flip-flops you would need to implement that finite state machine. All right, let's move on here. So we talked about the state encoding and the fact that we could have many different variations, but that actually affects our number of states. Now, if you think about this, if you have 4 states, how many flip-flops would you need for 4 states? Number of flip-flops. So take a moment here and think about a counter design. When you had a 3-bit counter, how many states did you have? How many states did you have over there? Right? For a 3-bit counter, the thing that we designed here, that was a 3-bit counter, right? And in which we were doing like an arbitrary counting sequence. In this particular counter, we had, let's see, 7 states. So when we had 7 states, how many flip-flops did we need? Now, if I go up further, I needed 3 flip-flops to do it, right? So for a 3-bit flip-flop, we needed a 3 flip-flop design. But the number of states could go up to 8. we were satisfied with 7. Now in this example, we have 4 states. So your answer is 2 flip-flops, and that's exactly correct. So we would need 2 flip-flops to do this. However, if somebody used all the 16 states for 0, 1 cent, 2 cent, and so on, then they would need 4 flip-flops to do it, right? So you can clearly see that there is a disconnect, or there is a significant difference in how much it would cost. All right, let's move on and spend some time talking about a Mealy finite state machine. Now in this particular structure, a lot of the things, in fact all the things, when you compare it to Moore, are exactly the same. The only difference is this. That's the only difference between a Moore and a Mealy machine. For a Moore machine, that wasn't there because there was no dependence of outputs directly to the inputs for Moore machine. However, for Mealy machine, we said the outputs can change when the current state changes or the input changes. So the only difference here is of that link there. That's it. That's the only difference. Everything else is the same. You still have a combinational logic over here, still have a combinational logic over here. You have all the flip-flops implemented right in the middle, and there is a feedback from the flip-flops back to the input, so that's how we implement memory, by using that feedback. And inside the state memory, we typically have edge-triggered D flip-flops. Now, what we can do is we can implement the same vending machine with the same state assignment. However, this time we will design it using a Mealy machine. So in a lot of these finite state machine designs, you have that option to go with a Moore-based design or a Mealy-based design. The only criteria that you need to take into account is whether you want that to respond immediately when the input changes, or are you okay with that machine responding to the changes after it reaches the current state. That's the criteria. So in this case, we are designing the same vending machine. We still have the 0 cents, 5 cents, 10 cents, 15 cents states, but notice what you are doing here. If you are in state 0 and you get a nickel, then you go to 5 cents, exactly the same way. However, as you are making that transition, your output has already become 0, right? So 0 cents, you get a nickel, you go to 5, but your output is 0 at that time. So the input, as soon as you entered the input, as soon as you change your nickel, the output became 0 right away. It did not wait for you to reach 5 cents. It became 0. So for a Mealy machine, there is a change in how we draw the state diagram. And as you can see, we are representing the current state over here. We are representing the input over here. So all of these are inputs in blue. Well, let me use this. Let me use this. What else? Right there. I think I've exhausted all the inputs. However, the output, you see where I'm indicating the output? The output is on the arrow or the arc, as opposed to being connected to the state, right? So this is simply input slash output. Input that caused the transition slash what happened to the output because of that, right? So that's the notation that we are using. So that's not divide by 0, that is just slash the output. So the way you would read it is So let's go through this like a straightforward path. You are getting a nickel, don't make the output, don't vend. Another nickel, don't vend. And as soon as you get a nickel or dime, vend it, right? So the vending is happening immediately after you get a nickel or a dime from 10 cents. You're not waiting for it to reach 15 cents, right? So the vending is happening as soon as you get that input. All right, so just a change in how the outputs are represented. Everything else is the same. Now you can keep them right next to each other to compare. On the left, we have a Moore design. How do you know that's a Moore design? Because I see the outputs are a function of the state. And on the right, I have the Mealy design. The outputs are the function of the arcs. So that means that they are dependent on the states, but they are also dependent on the input directly. And the good news is with a Mealy machine, you will have situations where you can simplify the design even further. So that's the best news here. And we will explore how we can simplify designs with a Mealy machine in just a bit. To do that, we will consider a Moore machine first, and then we will try to design a finite state machine for the same application, but a Mealy design. So first we'll start with Moore, and we'll see what the example is over here. We are going to consider a machine that asserts its output when the input has 2 or more consecutive ones. So if you are looking at a bunch of zeros or ones coming in, you are looking at one input there, and you are asked to observe the input, and if it has 2 or more consecutive ones, you are supposed to make the output 1. Sound problems? Is it okay now, or are we still having some issues? All right. Hopefully, so let me know if the issue happens again. So right now it looks like it is good for now. All right. So you guys see the idea here. Let's do a squared paper here. All right. So I have this finite state machine here. I have input and I have an output here. And if I talk about the input as a function of time, the input is say 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 0, right? What should be my output? Well, the output, you can start off as a 0. So the moment you see a 0 first, your output is 0 because no consecutive ones. After you see the first one, your output is still 0 because no consecutive ones. But after you see this guy, your output goes to 1, right? Because you said 2 or more consecutive ones assert the output. And then the chain is broken. 1 consecutive one, 2 consecutive ones. Oh, sorry, this needs to be a 0. 2 consecutive ones, 3 consecutive ones, 4 consecutive ones, chain broken, nothing, nothing, and nothing. You guys see this? You guys see what this is essentially to explain the desired behavior, right? So this is just to explain the desired behavior of FSM, right? So your input is coming on one wire, right? And there is a bit stream that is coming in on that one wire. your finite state machine needs to observe that bit sequence, and as soon as it sees two consecutive ones or more than that, it needs to make the output 1. That's the goal of this finite state machine. So it is trying to recognize a string of 2 or more ones. So that's the goal. And with a Moore machine, we can accomplish that with 3 states. The first state can be, I got a 0. The second state can be, I got a 0, 1. And the third state can be, I got a 1, 1. You guys see that? So those are my 3 states. Got a 0, then got a 1, and then got a 1, 1, or received a 1, 1. Now the question is, why did I not consider the got 1 state, and why did I not consider the got 1, 0 state? So question is, why is this not there, and why is this not there? That's right, it's unnecessary. 1, 0 is not there because 0 automatically breaks the loop. Yes, so got 1, 0 is the same as got 0, right? So that's good. That's a valid statement right there. That's a valid 1 is the same as 1 from 0, right? So 1 is the same as this guy. So we don't need to consider those. You guys are absolutely right. So I hope that you see why we chose these states, and you can write them in other words as well. Got 0 is the same as saying the last input was 0. Got 0, 1 is the same as saying last 2 inputs were 0, 1, and then last 2 inputs were 1, 1. So those are my 3 states. I don't need to worry about any more states with this. So when I got 0, my output is 0. When I got 1, let me erase this. When I input 0, input 1, not input, state 0. So this is state 0, state 1, state 2. Output is 0 because I just got 0. Output is 0 because I got 0, 1. Output is 1 because I got 1, 1. Now, if I am in state 0, that means I got a 0. And if I keep continuing, if I keep getting zeros, I will stay in that same state. That's a self loop. But if I got a 0 and I next get a 1, that will help me transition to the state which is got 0, 1, in which my output is still 0 because I need to get one more 1. And when I do, I will go to state 2 where my output becomes a 1. Now, if you are in state 2, which means you got 1, 1, and you get a 0, you break the loop and you go back over here. And if you are in state 2, which is got 1, 1, and you keep getting 1s, you will stay there and your output will continue to be a 1 because this is for 2 or more consecutive 1s. Now, if you are in got 0, 1 state and you get a 0, you go back because that is counting essentially as a got 0 state. Now, one thing you can notice here to make this a little bit more systematic is every state, the moment you sketch up these 3 states, these 3 circles, from every state, you need to consider the possibility of two inputs, right? So every circle has two arrows coming out of it. 0, 1. 0, 1. 0, 1. Right? So when you are in any state, you need to consider what could be the next input and where should I go for that particular input. All right, questions about how we draw the state diagram for this particular design. And while you guys are doing that, also think about how many flip-flops do I need to implement this? Number of flip-flops. All right, so 2 is the right answer, because with 2 flip-flops I can go up to 4 states, and I have 3 states over here, so I at least need 2 flip-flops to do this. So number of flip-flops are essentially log to the base n of the number of states. Those are your number of flip-flops. All right, let's go back to a Mealy structure. That's what Preston said. I'm going to go back here and just take a moment. So Preston, let me know when you're ready to move on. Do you want to talk about this a little bit, or what's going on? Do the inputs automatically change the outputs, or do they need to wait for the clock to update? Your first statement is correct. The inputs can directly change the outputs. They don't need to wait for the clock. Moore needs to wait for the clock. Mealy doesn't. That's the difference. That's the main difference between these state machines, the two types. And that's exactly why it's called asynchronous, because the moment input changes, the output can change. Hence, the flip-flop is not necessarily synced with the clock. Hence, asynchronous. Is this unnecessary for human operated? Well, that depends on the application, right? And that also depends on how much you are willing to invest in terms of space and cost for a design. I'm going to later show you that Mealy designs can be simplified and they are much more effective in terms of cost than Moore design. So there are benefits of considering a Mealy design, other than just the speed of the response. In some cases, you would want to have that speed. Moore needs to wait for the clock to change input. Not to change input, change output. So the Moore machine outputs can change only after there is a change in the state, which means it is dependent on when the state changes. And we know that flip-flops can have a change of state only after the active edge of the clock. So the outputs for Moore can only change based on the clock. Hence, they are called synchronous with respect to clock. But for Mealy, the inputs change. That means that change goes through this. This is combinational, so the outputs can change. They don't need to wait for this to go from the current state to the next state. They could, but it's not necessary, right? So Mealy has both types. So it's like Moore plus a dependence on input directly. All right, we can come back to it if you guys have more questions about that. Let me move on to our consecutive ones detector. So we are trying to detect two or more consecutive ones. This was a Moore-based design, and you guys said that we need 2 flip-flops to do this. Now we talked about the behavior. Now let us consider the alternative. The alternate is to design the same machine, but based on a Mealy characteristic. So in this case, I only need 2 states. If I am in state 0, and if I get a 0, I will continue to be over here, and my output is a 0. So input is a 0, output is a 0, and I stay there. If I get a 1 from state 0, I go over here. So this is like got 0 and then got a 1. That's it. Those are the 2 states. So if you get a 0 and then your next input is also a 0, you stay there. If you got a 0 and your next input is a 1, your output is still a 0, but you go to state 1, which is got 1. If you are in state 1, which means you got a 1, and you get another 1 or more than 1, you stay there and your output is 1. And the moment you get a 0, your output becomes a 0 and you go back to state 0. Now you see why how are we able to do this in 2 states? And we were not able to do that in 2 states over here. Why was that possible with Mealy machine? What is that one change that made this possible, that we are able to do it in 2 states? Outputs on the arcs, absolutely right. The outputs are now function of the arcs as opposed to being limited to the states. That is what is making it possible. No, that's right. The outputs being a function on the arcs, that's what makes it possible. If I limited it to the states, then I could only have an output there and an output there, right? So I would need more states to encompass the 2 or more consecutive criteria. But I don't need to worry about that here because now I have made the outputs as a function of the arcs as opposed to a function of the states. All right, questions about how we were able to design this 2 or more consecutive ones machine using Moore and using Mealy. Now when we design this, you will only need 1 flip-flop to do it because you only have 2 states. Now, you know what is what can be a little bit tricky over here is the notation. So let me just point out, this is the input that is causing that transition, and that is the output. Can you explain the dependencies of the outputs, Moore versus Mealy? Okay, so for that I will have to go back to this. All right, let me erase this guy. Now I want you to answer this. If this is combinational and this is sequential and this is combinational, if you consider this particular structure, think about when can this change. Now, if you look at this combinational block has 2 types of inputs. One is directly coming from the inputs to the machine, for example, the nickels and the dimes. And the other type of input is from the sequential elements of our state machine, which are D flip-flops. So if you had both these connections, then your outputs can change when the current state changes to the next state or the inputs change anytime. And we know that the outputs of flip-flops only change based on the clock because they are edge triggered. However, inputs, these are in the user control, so that can change anytime the user wants, and you would change the outputs. For a Moore machine, this is not there. So you would have to go through the state memory in order for the outputs to change. So the question is, but don't Moore machines depend on state and input? Oh, yeah, right. Absolutely right. They do depend on the state, which depends on the input originally. So there is dependence on the input, but it is precisely not the input, it is the sequence of past inputs, right? So Moore depends on a sequence of past inputs. But Mealy depends on inputs. That's the difference. Because as you are changing the input, your current state would change, then it would change the output for Moore, right? You see the difference now? So it also depends on sequence of past inputs here, because there is also a dependence on current state. Wouldn't the same inputs have different outputs? Well, that depends on which state you're in, right? From every state, you are getting many arrows out of them depending on the input-output combination. All right, we can come back to this slightly later after our class time ends if there is a need to do this. But I feel like if you zone in on this statement, Moore depends on sequence of past inputs and Mealy depends on inputs as well as sequence of past inputs. That's the key there. All right, let's move on to. All right, so now if you look at the detector, right, the two or more consecutive ones detector for Moore and Mealy, and you compare them, Moore required 2 flip-flops, Mealy required 1 flip-flop, and a more effective design, fewer states, fewer flip-flops. So the designers are more likely to prefer Mealy because of that reason. Moore required more, yes. That's a very good way of kind of remembering that. All right, let's move on. Now let's come to a more straightforward discussion, which is to reverse engineer a finite state machine. So the goal over here is that you may be given a finite state machine and you are supposed to analyze it, right? So this is sort of FSM analysis as opposed to design. So given an FSM, you come up with what it is doing. That means you are essentially supposed to draw the state diagram given the circuit, right? So something like, if I go back to our counters design, given this, you're supposed to sketch that, right? So it's the opposite way. So let's try to see that. Let's try to see how we do reverse engineering or finite state machine analysis. And for this, we will consider a Moore machine first. And can you guys spend a minute or so looking at this circuit and telling me how do you know it's Moore? Like, what makes it classify as Moore? Input does not directly link to output. Okay, the input from XOR gate requires that output is only affected by clock. Okay, that's good. They must go through the sequential circuits. Okay, all good. The way I would answer this, most of your answers are all on the dot here. I would see this. Output is Z, and output equals the flip-flop output. If Z equals the flip-flop output, and that's the only dependence, then I know that it is linked, the output is linked to the state of the flip-flop and not directly dependent on the input X. That's how we can classify that as a Moore machine. Our input is X for this design, and that is coming in over here, over here, over here, over here. And there are two states A and B, that go here, 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 and here. That's it. We have two flip-flops, flip-flop A and flip-flop B. Now what we are going to do is we are going to use characteristic equations of the flip-flops to complete this reverse engineering finite state machine analysis. And because we have JK flip-flops in this design, I would need to kind of review the JK flip-flop characteristic equation. And the characteristic equation of a JK flip-flop is Q plus equals JQ complement or K complement and Q, where Q represents the previous state or the current state, and Q plus represents the next state. And Q is current state. And of course, J and K are the inputs to the flip-flop. So let's do this problem. What I'll do is I will add a slide here after, and just so that I have this, I'm going to take a picture of this guy. Let's see, take a screenshot, sure. And then paste it over there. All right. Next, let us focus on flip-flop A. Small a, sure. Let us focus on that. So using the characteristic equation that we just wrote here, Q plus equals JQ bar plus K bar Q, let us do that characteristic equation for flip-flop A. So what would that mean? It would mean A plus equals J, let me use A, all right, JA JQ bar or K bar Q. You guys agree with this? Now our state is A and B, so our Q plus and Q are replaced with A plus and A. JA and KA represent the J and K inputs of flip-flop A. Do you guys are you guys okay with the equation at the top of the screen? So I'm just using this guy right there. It's the same one. But for flip-flop A. Why can't you substitute? I'm going to do that. But I'm going to go through that in a step-by-step manner. Yes, absolutely right, Ian. That's where we are going with this. All right, let me erase that. I did not hear any feedback about the first statement, so I'm going to assume that you guys are good with it. Now let us do this. What is JA? Like Ian said, it is directly connected to the input X. What about KA? What is that? X and B complement. Wonderful. Now I can substitute these back into my equation. So A plus is going to equal X and A complement, or X and B complement, the entire thing complemented, and A. X, A complement, let's do this, X complement and A, or B and A. So let me write down this answer here. Actually, just do A plus and then box it up. You guys okay with that expression right there? Now I'm going to do the same thing for flip-flop B. Let's do it over here. Flip-flop B. B plus equals JB and B complement, or KB and KB complement and B, which is essentially going to equal JB is X and B complement is B complement, can't do anything there, or KB complement. What is KB complement? This is X exclusive or A complement, and the entire thing needs to get complemented, or and B complement. That will equal X and A complement, or X complement and A and B complement. Is it B complement? Oh, just B. All right. If you guys don't agree with any step, let me know and I can clarify. All right, I see that there is a B complement. No, there is a X here and here. They both have X. So I can write this as X, and do you still need to complement the exclusive OR part? Yeah, so I did, right? So if you look at this, X exclusive or A complement, the entire thing complemented, is simply X exclusive or A. All right, who can tell me what this is? B complement or A complement and B? What does that simplify to? Not A and not B is absolutely right. Yes. That's absolutely right. So I need to continue here. So I'm going to grab this and move to the next page. So this is, all of this is for B plus. All right, so now let's see. This is going to be X and B complement, or X and A complement, or X complement and A and B. Let's just write it that way. That's, I don't think we can do anything here. So just let's write this in I think this is the best we can do here. Let me box this up. Oh. All right. What else can I do here? Come on. I've written an expression for A plus. I've written an expression for B plus. Now I need to write an expression for the output. What is Z? What is the expression for Z? Output Z. Z equals B, right? So that's just that. Output Z equals B. I'm also going to box this up. Could we have just used K-maps when it was in SOP form? Yes, you could have used as K-maps as well. You're absolutely right. You could have. Now, I hope you guys are okay with the three things that we did here. One, write an expression for A plus. Second, B plus, and output Z, right? In general, what would that be? In general, it would be write simplest. Simplest is fine, but what we are really after is write logic expressions for the next state variables and output or outputs in terms of inputs and current state variables. So we have written an expression for A plus, B plus, and the output Z in terms of input X, current state variable A, current state variable B. The next thing is to write the state transition table. And the state transition table has a particular form. Let me show you guys how that is. So I'm going to sketch up a big table here, and I'm going to divide it up into 4 sections. 1, 2, and 3, 4. All right. And then on the leftmost column, I'm going to include my present states, input, next states, and then output. So let me write this down here. This is present states, input or inputs. In this case, we only have one. Next states and outputs. In this case, we only have one, so output. Now, when you say current state, present state or current state, A and then B, how many different combinations can I have for A and B for a different X? So my present state could be a 0 and a 0 here, and my input could be a 0. Present state could be 0, input could be a 1. Present state could be a 0, 1, input could be a 0, 0, 1, input could be a 1. You see how we are filling this up? We are essentially filling this up as a truth table, right? Alternates every time, alternates at half the frequency, alternates at half the frequency of that. So from here, we can just fill it up directly. We got 0, 1, 0, 1, and then let's see, 0, 1, 0, 1. And then we got 1, 0 here, 1, 0 there, and then 1, 1 there, and 1, 1 there. So present states and input, that is essentially classifying as the input to the state transition table. Now, can we somehow fill up the next 3 columns, A plus, B plus, and Z? You can, right? Because we have the logic expressions that we just derived here. So by using the logic expressions that we just derived for A plus, B plus, and Z, you can fill out the other 3 columns in this case. Let us start with the simplest one, which is Z equals B. So I'm just simply going to copy this guy and paste it over here. So that is Z equals B. That's done. And then what I can do is A plus and B plus. Let's see which one is easy. A plus X A complement or X complement A. Okay, so let me just fill this out. You guys can verify this later. I'm just using the logic expressions for A plus and B plus and plugging in the 3 variables A, B, and X into those equations to find out A plus and B plus. Let's see, I got 0, 0, then 1, 1, then 1, 0, and then 0, 1, and then 1, 1, and then 1, 0. So I've essentially used the logic expressions derived earlier to fill these 3. The next thing on my list is to define the states. So what I'm going to do is I'm going to observe that over here A is 0 and B is 0, which also happens over there, and that's it. So that can be my state 0. Then I'm going to do the same thing for 0, 1. Where is 0, 1? It's right here. That's it. That can be my state 1. 1 0. Here, here, that's it. State 2. Last one. Here, here, and here. State 3. I guess now I can ask you the question, how many flip-flops do I need to synthesize this? Yeah, absolutely. You see that? Those two are right there. All right, let's, so here I can say obtained using derived equations. All right. Hard work is almost done. The only thing that is left over is to draw the state diagram. So let us do it over here. Let's do it over there. So the first question you would ask is, how many states did we have? And clearly we had 4 states, S0, S1, S2, S3. So right there you would say, I need to draw 4 circles. All right. Let's draw 4 circles here. And then this can be S0, oh, come on. S1, I can make this S2, and I can make this S3. Now, if you are in state 0 and you get a 0, if you are in state 0 and you get a 0, you stay there. You are still in state 0. So that would correspond to me drawing a self loop. By the way, in state 0, I should probably just move them inside. So if you are in state 0 and you get a 0, you stay there, right? You see how I'm writing this? 0 0, I get a 0, I stay there, 0 0. If you are in state 0 and you get a 1, you go to 1 1, which is state 3. All right, I'm done with both the situations for state 0. Now let's go on to state 1. And I hope that you guys can pitch in. So if you are in state 1 and you get a 0, where do you go? If you are in state 1 and you get a 1, where do you go? If you are in state 2 and you get a 0, where do you go? State 2, input is 0, you stay there. State 2, you get a 1, where do you go? S1. State 3, you get a 0, where do you go? State 3. Oh, sorry, 0. State 3, you get a 1, where do you go? State 2 is right. That is your finite state machine. So we started up with a flip-flop based design. You were given the circuit. From that circuit, we derived the next state equations using the characteristic equation of the flip-flops that were involved. Then we wrote the state transition table, in which we had 4 main columns: present states, inputs, next state, outputs. And then the last thing that we did was, using the state transition table, we sketched up the state diagram. Questions about this process? There are no sort of, this kind of a question on finite state machine analysis, the reverse engineering problem. You should definitely expect a problem on this on the final exam. There's absolutely no points for guessing that. All right, now let me make this a little bit more complex for you. Let me go over here. So we did this example. Let me continue and look at this. The next example, we are not going to go and do the same sort of examples every time, but I just want you guys to recognize that you could, given the time. So in this particular finite state machine design circuit, we have inputs X and Y. Your states are A and B, and the output of the flip-flop is Z. First question first. Is this a Mealy machine or is this a Moore machine? Mealy is right, because Z depends on X and Y through this combinational circuit. So I hope you guys are able to map this to that. You guys see that? And let us also map this. Let us map this guy. This is the next state logic, F. Where does that exist in this? It is all of this. The sequential parts right here, the JK flip-flop. So I hope you start recognizing the structure, given the structure of your. All right, so it's going to become simple, Preston, in a hurry. Because you know what? You guys, this guy is 8:1 marks. These are 2 to 4 decoders. These are NAND gates, these are NAND gates, these are JK flip-flops, and that's it. And this 8:1 marks, if you go back and look at what you did for your midterm exam, you guys actually analyzed a very, very similar 8:1 mux. You actually analyzed it. So you essentially wrote the expression for the output in terms of the inputs A, B, X, and Y. You did that in one of your exam 2 problems. So you can check that. So you have got a 8:1 mux, and we know how to write an equation for the output there in terms of its inputs. In this case, A, B, X are my select lines, and D7 all the way to D0, those are my data inputs. So it's selecting one from all the others. Looking at this circuit, is it okay to have no idea what its function is? Absolutely, absolutely. When you look at this, I'm hoping that if you did, then you have a very, very special skill. I don't know what it is doing right now. The only way to do this is, let me write the steps here. The first step would be write an expression for the output of the mux. Write an expression for the output of the 2 to 4 decoders, because I know that 2 to 4 decoders, the outputs are max terms. We know that when we talked about the decoders. Then using the equation for the mux and the two equations of the 2 to 4 decoders, I would then connect them to the JK flip-flops. Now once I get to that stage, I'm going to use the characteristic equation of the two JK flip-flops to write the expressions for A plus and B plus. The last step would be to write an expression for Z, and that particular combinational circuit will give me that. Right? So it's going to be step by step. You would write an equation for here, then you would write an equation for this and this, then you would write an equation for essentially your JA and KA and JB and KB. Your objective, write an expression for A plus, write an expression for B plus, and then write an expression for Z. Once you write those expressions, then you would go fill in the state transition table. From the state transition table, you would draw the state diagram. So the results are actually provided to you on these slides. However, for me to kind of go through these, it's just redundant. So I want you guys to spend a little bit of time looking at whether you are able to do these steps or not, because this sort of a problem you should absolutely expect on your exam, because this allows me to test muxes, decoders, finite state machine analysis, characteristic equation of the JK flip-flop. So one problem attacks so many different concepts. So I hope that you guys are able to look at this design. These are available on these. If they are not available on Piazza, I will make them available very shortly. But you should try to see if you can get these results. Once you get these results, then try to, from the state transition table, try to draw the state diagram. The answers are available, but you can definitely use this as a very, very good practice. So the thing on the exam will not be as complex, or in terms of size, it'll not be as big. But for practice, I think there's a good example here. All right. I think it's a good place to stop. I am going to say a few things before we go off to the break. Let me just stop recording here for a minute.